So what I'm doing here is trying to show you the geometry of difference quotients. They come up a lot. They're pretty important. We use them to approximate slopes of curves. So if I want to find the slope or approximate the slope of this curve, f of x, which is x plus sine of x, at the point A, the x-coordinate of A is 1.5. One of the options that I have is a symmetric difference quotient. So what I'm doing is I've set h to be 1. So I'm moving 1 unit to the right of A, which gives me 2.5. And I'm moving 1 unit to the left of A, which gives me 0.5. And then I'm going to find the slope of the secant line, which is the line passing through these 2 points. And I'm just going to use that as an approximation. So you can say I get 1.06. Now, what you typically do is you then let the points get closer to each other. So I did that by a factor of 10. Now I have a slope of 1.07. You can see the points are much closer to A. So, I mean, it should feel a little intuitively like you're getting really close to the slope, 1.07. So you can see the 2 decimal places, that didn't even change when I changed A. Now, curiously, GeoGebra is going to round this to 0. But 1.07, you can see from the graph, it really does appear that the 2 points are so close to A that they're indistinguishable at this point. So that slope through those 2 points is a really good approximation of the slope at A. And of course we have other options. So that's symmetric, you move 1 in either direction. We can do what's called a right difference quotient, which is by far the most popular. And so h is, I reset it to 1. So you can see what I'm doing is I'm taking a point to the right of A, which is why it's called a right difference quotient. And what I'll do is I'll just let this point get closer and closer to A. And the way that I do that is by letting h get smaller. And ultimately, so you can see that the slope got a little more extreme there. 0.1, that's 1.02. It's close to what we were getting before. 0.001, 1.07. I don't think I can improve on that because it's already rounding to 0. 1.07, which you might recall is the same as what I got before with my symmetric difference quotient. I have a lot of trouble saying that. And then a third thing that I can do is a left difference quotient, which I find not to be quite so common. But starts here, so here's the point we're interested in is A, and then we move h units, in this case 1, so 1 unit to the left, find another point, and draw the secant line, find its slope, and use that as an approximation. So h being 1 would be a huge value for h. 0.1 is even a large value for h, because ultimately what we're going to do is we're going to look at the limit as h approaches 0. I mean, that's what I'm doing when I replace these values. I'm just making h smaller and smaller. So h is approaching 0. GeoGebra there makes h 0, which is really weird. I mean, it's rounding, so this fraction here looks ridiculous from an algebraic standpoint. But from a calculus or limit standpoint, I mean, I guess we're kind of okay with that, but it's really just an artifact of the rounding. 1.07 again. So actually what happened was, for each of them, now I'm getting some wonderful, now apparently it's actually made it into 0, which caused that problem. You can actually see that all 3 of them have the same limit as h approaches 0, which is an interesting thing. The symmetric difference quotient can actually get fooled by this process because of the way that it works, and we'll talk about that in greater detail at some point. But anyway, that's the geometry involved in difference quotients. We're really just making secant lines and looking at their slopes. So I hope you find that helpful in understanding what's going on. Good luck.